Good evening. You are tuned to the Cosmic Lullaby Channel. Tonight, we are not just telling a story, we are launching a strategic analysis, an investigation into a geopolitical dynasty that held the world in its grip for a period so vast it defies human comprehension. We are journeying back, not merely through the mists of time, but into a lost epoch of planetary dominance. This was a world that operated under a different global order, a planet that looks nothing like the one we know today. Forget the familiar maps of our modern age. This was a time when the continents themselves were locked in a slow, inexorable dance of separation, forging new oceans and mountain ranges. Vast primordial forests stretched from pole to pole, a green empire untouched by human hands. And beneath the canopy of these ancient woods, the very ground shook, not from seismic tremors, but from the footsteps of the largest terrestrial creatures the world has ever known. This is the chronicle of their lost world. This is the story of the dinosaurs. They were more than just colossal beasts with teeth and claws. They were the architects and undisputed rulers of their age. The term dinosaur itself, born from the Greek words deinos and sauros, meaning terrible lizard, is a profound miscalculation, a historical artifact from an era when our own understanding was in its infancy. Coined in the mid-19th century by Sir Richard Owen, the name reflected the limited data of the time. Scientists confronted with fossilized bones of immense reptiles could only imagine them as gargantuan versions of modern lizards, slow, cold-blooded, and primitive. As the archives of stone were pried open, as more fossil evidence was unearthed from the Badlands of North America to the deserts of Mongolia, it became devastatingly clear that dinosaurs belonged to their own extraordinary branch of life, a strategic diversification that rewrote the rules of biology. Unlike the sprawling posture of modern lizards, their limbs were positioned directly beneath their bodies. This was not a minor anatomical tweak. It was a revolutionary leap in biomechanical engineering, granting them a powerful, upright posture built for sustained movement, for migration, for pursuit, and for dominance. Their physiology was a masterclass in adaptation. The architecture of their hips, their hyper-efficient respiratory systems, which we will analyze later, and their metabolic growth rates were fundamentally distinct from the reptiles we know today. In a twist of evolutionary fate that continues to challenge our classifications, dinosaurs are more closely related to the birds flitting outside your window than to any lizard or crocodile. The name terrible lizard stuck, a relic of initial misjudgment, but the dynasty it describes was far stranger, more diverse, and more astonishingly successful than anyone had first dared to guess. Their empire stood for over 160 million years. Let that number settle in. It is a timescale so immense that the human mind struggles to build a framework for it. Our entire species, Homo sapiens, has existed for a mere few 100,000 years. Our recorded history, our empires, our wars, our technological revolutions is a fleeting footnote spanning just a few thousand. By contrast, the dinosaurs presided over an almost eternal reign. To put their tenure into geopolitical perspective, their dynasty lasted roughly 800 times longer than the Roman Empire. During their time on the throne, entire continents drifted apart, reshaping the global map. The supercontinent of Pangaea fractured, creating new oceans and isolating populations, which in turn drove an explosion of evolutionary diversification, a biological arms race on a planetary scale. Climates shifted dramatically from lush global swamps to arid, sprawling deserts. And through every environmental crisis, every geological upheaval, the dinosaurs did not just survive, they adapted, they diversified, and they thrived. They colonized every terrestrial ecosystem, from the tropical forests of the equator to the temperate woodlands near the polar regions, which were then green and vibrant. The sheer longevity of their dominion is a testament to their success. They were not failures or evolutionary experiments doomed from the start. They were, by any objective measure, among the most successful and resilient dinosaurs of animals ever to inhabit this planet. By comparison, humanity has only just arrived at the party, a brash newcomer on a stage where giants once walked for an eternity. The faint imprint of a footprint left in mud that hardened into stone is not just a fossil. It is a seal of office, a remnant of a power that once held the entire world as its territory. The bones we now unearth are the fallen columns of their forgotten empire. When we analyze the strategic framework of the Dinosaurian dynasty, the most striking feature is its breathtaking scale of diversification. This was not a monolithic empire of giants. It was a sophisticated global power that mastered every conceivable ecological niche. When we imagine dinosaurs, our minds often gravitate toward the titans, the colossal predators and the long-necked sauropods that could blot out the sky, the equivalent of geopolitical superpowers. But this picture is dangerously incomplete. To understand their success, we must examine the full spectrum of their operational assets, from the strategic heavyweights down to the small, agile operatives that thrived in the shadows. Some of the most compelling fossil evidence reveals species smaller than a modern chicken. The discovery of small theropods like Microraptor has revolutionized our understanding, presenting us with creatures scarcely 2 feet long, light enough to scamper up trees or glide between branches like phantoms in the prehistoric undergrowth. These were not failed giants, they were specialists. Agile, quick, and likely possessing a high degree of situational awareness, they were the covert hunters of insects and small prey, operating in environments inaccessible to their larger cousins. Fossilized feathers preserved in amber and fine-grained stone show that some of these miniature dinosaurs shimmered with iridescent colors, turning them into dazzling bird-like jewels of the forest floor. This wasn't just for aesthetics. It was a complex system of signaling, camouflage, and species recognition, a silent language spoken in flashes of light. These tiny dinosaurs demonstrate a core principle of enduring power: total market saturation. They prove that the dinosaurian empire wasn't just about projecting overwhelming force through size. It was also about precision, subtlety, and the complete colonization of every available resource, no matter how small. They filled every role, from towering mobile fortresses that consumed entire forests to delicate feathered miniatures that darted through the ferns. So when you hear the word dinosaur, it is an analytical error to only picture the giants. To do so is to see only the battleships of an empire while ignoring the intelligence agents, the supply lines, and the economic infrastructure that truly sustained it. They filled every role, from towering mobile fortresses that consumed entire forests to delicate feathered miniatures that darted through the ferns. So when you hear the word dinosaur, it is an analytical error to only picture the giants. To do so is to see only the battleships of an empire while ignoring the intelligence agents, the supply lines, and the economic infrastructure that truly sustained it. The overall mood of this strategic spectrum, we confront the absolute limits of biological engineering. We must confront the titans. Imagine standing on an airfield, looking up at a Boeing 747 jumbo jet, fully loaded and ready for takeoff. Now imagine a living, breathing creature of flesh and bone that rivals that machine in sheer mass. This is not science fiction. The largest known dinosaurs, the colossal sauropods like Argentinosaurus and Patagotitan, reached weights that paleontologists conservatively estimate at over 70 tons. This is more than a fully loaded 747 airliner. Yet these were not machines of metal and wire. They were living organisms, creatures of bone, muscle, and sinew that had to find food, evade predators, and reproduce. The physiological challenges are staggering. Their hearts, massive pumps of muscle, had to generate enough pressure to force blood up necks as long as a school bus, defying gravity with every beat. Their skeletons, though immense, had to be both strong enough to bear unimaginable weight and light enough to allow movement. The solution to this paradox was an evolutionary masterstroke. Their bones were not solid. They were filled with a complex system of air sacs, much like the skeletal structure of modern birds, which dramatically reduced their weight without compromising their structural integrity. Their respiratory system was a model of efficiency, utilizing these same air sacs to create a unidirectional flow of oxygen through the lungs, a system far superior to the simple in and out breathing of mammals. The overall adaptation was critical. It was the engine that fueled their massive bodies, allowing them to extract enough oxygen from the atmosphere to power their continent-crossing movements. And they did move. They thundered across vast floodplains and through primeval forests, their footsteps creating seismic tremors that literally shook the ground as they walked. These dinosaurs were the heaviest land animals that have ever lived, period. Their very existence is a profound statement on the power of evolution, a demonstration of how far life can stretch the boundaries of what is physically possible when given enough time and resources. They represent the pinnacle of natural engineering in terms of scale, living proof that on the ancient Earth, giants not only walked, they reigned. They were the ultimate expression of biological power, the living, breathing capital ships of the dinosaurian age. In any enduring global dynasty, power is not maintained by a single strategy. While the colossal sauropods projected an image of overwhelming size, the Mesozoic era was also defined by a high-stakes perpetual arms race, where speed and defense became critical strategic assets. The battlefield of the ancient world was not just populated by lumbering giants, it was also a high-speed environment where agility could mean the difference between life and death. Though many dinosaurs were huge and seemingly ponderous, some were engineered for pure velocity. Lightweight theropods, such as the ornithomimids, were the Mesozoic equivalent of fast attack vehicles. Fossil reconstructions of their anatomy reveal a masterclass in biomechanical engineering for speed. They possessed long, slender legs built for a powerful stride and stiff, rigid tails that acted like sophisticated balancing rods and rudders during high-speed maneuvers. This was not a passive feature, it was an active guidance system. Biomechanical models based on their fossilized skeletons suggest that some of these animals could achieve speeds of over 40 miles per hour, making them faster than a human sprinter at the peak of Olympic performance. Imagine the strategic implication. Herds of these sleek, ostrich-like dinosaurs dashing across ancient plains, their tails streaming behind them as dynamic stabilizers, their feet kicking up dust in rhythmic, powerful bursts. In this ecosystem, speed was their primary defense system, a preemptive countermeasure that allowed them to outrun even the most formidable hunters. Their entire physiology, the hollow bones for reduced weight, the powerful leg muscles, the stabilizing tail, points to a life lived on the edge, a tensed balance with predators where survival was measured in milliseconds and inches. They remind us that in the grand strategy of evolution, overwhelming force is not the only path to success. Agility, evasion, and rapid response were sometimes the most effective survival tools, a doctrine of speed that proved successful for millions of years. However, where speed was not an option, another evolutionary path emerged, the doctrine of overwhelming defense. This is the story of the living fortress. Enter the ankylosaurs. These creatures were, by any definition, biological tanks. Their bodies were encased in a formidable layer of thick, bony plates known as osteoderms, which were fused directly into their skin, forming a shield so robust it could withstand the most ferocious assaults. Some of these plates even bore sharp ridges and spikes, adding an extra layer of deterrence, a form of reactive armor designed to punish any attacker. The structural integrity of this defense system was so profound that scientific analysis suggests even the bone-crushing bite of a Tyrannosaurus rex, a force capable of pulverizing bone, may have struggled to breach it. This is not mere speculation. Fossilized ankylosaur armor sometimes shows healed bite marks, the scars of survived encounters, physical proof that they engaged with apex predators and walked away. They were mobile bunkers, slow-moving but nearly impregnable fortresses roaming the late Cretaceous landscape. As if this passive defense were not enough, the ankylosaurs developed one of the most remarkable weapon systems in natural history. Many species wielded heavy tail clubs, a solid mass of fused bone that could be swung with devastating kinetic force. This was not a simple bludgeon, it was a sophisticated piece of biological ordnance. Biomechanical studies indicate that a direct blow from an ankylosaur's tail could shatter the leg bones of a predator, crippling even a multi-ton tyrannosaur. This turned the slow-moving herbivore from a passive target into a dangerous combatant, capable of not just absorbing an attack, but delivering a decisive, bone-breaking counterattack. The evolution of the tail club, which appeared late in their history, points to an escalating arms race between predator and prey. A deadly feedback loop where T-Rex's devastating bite was met with the evolution of impenetrable armor and a bone-shattering hammer. The ankylosaurs serve as a dramatic reminder that in the unforgiving calculus of survival, defense can be every bit as awe-inspiring and strategically critical as offense. The evolutionary arms race of the Mesozoic did not produce a single one-size-fits-all solution to the problem of survival. While the ankylosaur perfected the strategy of the nearly invulnerable, slow-moving fortress, other lineages developed entirely different defensive and offensive platforms. Consider the Stegosaurus, one of the most iconic yet enigmatic dinosaurs to have ever lived. With its tall, bony plates rising like sails from its spine and its fearsome tail tipped with deadly spikes, it presents a fascinating case study in evolutionary priorities. For all of its impressive and intimidating hardware, the Stegosaurus possessed one of the smallest brains relative to its body size of any known dinosaur. An adult weighing several tons, a creature of immense physical presence, carried a brain scarcely larger than a walnut. For decades, this paradox puzzled paleontologists. Some early and now discredited theories speculated that the Stegosaurus must have had a second brain located near its hips to manage the complex motor functions of its massive rear body and tail. Modern analysis, however, suggests this wasn't the case. Instead, the limited processing power likely indicates a slow, deliberate, plant-focused lifestyle that did not require complex social structures or sophisticated hunting strategies. Its survival was not based on cleverness, but on its formidable defensive array. The large plates on its back, long thought to be purely for defense, may have also served as thermoregulatory devices, natural radiators to dissipate heat, or as dramatic display structures for attracting mates. But its primary weapon system was located at the end of its muscular, flexible tail. This weapon, a cluster of long, sharp spikes, has been given a unique name in the annals of science: the thagomizer. The term was playfully coined in a 1982 Far Side cartoon by Gary Larson, but has since been adopted by paleontologists in formal scientific literature. These spikes could reach several feet in length, and fossil evidence, including puncture wounds on the bones of predators like Allosaurus that perfectly match the spike's dimensions, provides undeniable proof that they were used in combat. Imagine this creature swinging its powerful tail in wide, sweeping arcs, the spikes cutting through the air like lethal spears. Any predator foolish enough to close the distance risked impalement. The Stegosaurus is a vivid reminder that in the calculus of evolution, intelligence is only one of many paths to success. Sometimes superior weaponry can compensate for a lack of strategic planning. Further down the timeline, in the closing chapters of the Cretaceous period, defensive strategy evolved again, producing what might be considered the heavy cavalry of the dinosaur world, the Triceratops. Instantly recognizable by its massive shield-like frill and 3 distinctive horns, this animal was a master of forward-facing, active defense. The 2 horns above its eyes were not for mere decoration, they were formidable weapons. Growing over 3 feet long and curving forward like polished spears, they were built for combat. The fossil record serves as a forensic report, showing clear signs of battle damage: skulls with wear patterns, deep scratches, and even healed puncture wounds, suggesting that Triceratops actively used these horns in high-stakes engagements. These were likely used in deflecting the attacks of apex predators like Tyrannosaurus rex, but also in ritualized duels with rivals of their own kind, locking horns in displays of dominance over territory or mates. Imagine herds of these magnificent beasts, their horns clashing in violent contests, or a mother lowering her head to create an impenetrable wall of spikes to shield her young from danger. The wide, bony frill, while offering some protection to the neck, was also likely a crucial tool for visual communication. Streaked with blood vessels, it may have been flushed with bright colors to signal age, health, or readiness to mate, turning the dinosaur into a living billboard of its own vitality. A natural male narrator with a warm, friendly tone. Speak at a moderate, conversational pace, fluid and easy to follow, like a light science podcast. Keep your voice clear and coherent with a gentle intonation that is both intelligent and soothing. Use pauses when necessary. The overall mood should be relaxed, engaging, and comfortable, perfect for bedtime reading and space narration. The tempo should be around 0.90. Elegant yet deadly, the horns and frill of the Triceratops transformed it into both an armored guardian and a dynamic symbol of power, a testament to a defense strategy based not on passive endurance, but on direct, aggressive, and overwhelming confrontation. Empire's dominance is not solely determined by its military hardware. It is equally dependent on its logistical infrastructure and its efficiency in resource processing. In the Mesozoic world, the most fundamental resource was food, and the dinosaurs evolved remarkably sophisticated technologies for acquiring and breaking it down. When you picture a dinosaur's mouth, you might imagine the simple, terrifying daggers of a predator. But some of the most advanced biological machinery was found within the jaws of the herbivores. The hadrosaurs, the so-called duck-billed dinosaurs, were masters of vegetation processing, and their success can be attributed to an astonishing dental arrangement. They possessed some of the most complex chewing systems ever seen in a reptile, a technology that allowed them to grind through tough, fibrous plants with an efficiency that rivaled the most advanced mammalian herbivores that would evolve millions of years later. Their broad, flat snouts, which earned them their nickname, were perfect for cropping and stripping vegetation. But the real work happened inside. Their jaws were packed with hundreds of teeth, arranged in intricate, overlapping rows known as dental batteries. In some species, the total tooth count exceeded 1,000. These were not individual teeth working in isolation. This was an integrated system. Imagine a biological assembly line, where rows of teeth worked in unison to slice, shred, and pulverize plant matter. As the outer teeth wore down from the constant grinding, new teeth were always in reserve, waiting in line below to emerge and take their place. This system functioned like a perpetually sharp grinding mill, a giant food processor that gave the hadrosaurs a critical advantage. They could consume and extract nutrients from coarse vegetation that would have been indigestible for many other herbivores. This dental superiority was a key strategic asset that allowed them to flourish across continents, becoming one of the most widespread and successful dinosaur groups of the late Cretaceous. They prove that in the grand game of evolution, internal technology can be just as decisive as external weaponry. This principle of endlessly renewable tools was not limited to the hadrosaurs. It was a core logistical advantage built into the very biology of many dinosaur species. Unlike mammals, including humans, who were issued only 2 sets of teeth for their entire lives, many dinosaurs replaced their teeth constantly, ensuring they never ran out of functional equipment for feeding. For an apex predator like Tyrannosaurus rex, whose entire strategy depended on its bone-crushing bite, this was a non-negotiable requirement for maintaining combat effectiveness. Its teeth were not delicate knives. They were thick, serrated railroad spikes designed for extreme pressure. The wear and tear from crunching through bone and armor was immense. Yet, this was never a liability. New teeth were perpetually forming within the jaw, ready to cycle forward and replace old, damaged, or broken ones, sometimes as frequently as every few weeks. Fossilized jaws clearly show this conveyor belt system, with rows of teeth in various stages of growth, a testament to a biological system designed for constant peak performance. This adaptation meant that no matter how demanding their diet or how violent their encounters, dinosaurs always possessed sharp, functional weaponry. It was a built-in system of maintenance and resupply, a logistical miracle that eliminated a key vulnerability. This remarkable feature is still present in their distant relatives, like crocodiles, providing a living link to the biological superiority of their ancient cousins. For the dinosaurs, teeth were not a finite resource. They were renewable assets, as essential to their long-term dominance as their claws, their armor, or their sheer size. It was a simple but profoundly effective system that underpinned their 160 million year reign, a quiet internal advantage that ensured the tools of survival were never allowed to go dull. Success on the battlefield, whether ancient or modern, is not merely a function of superior hardware. It is also a matter of intelligence, strategy, and communication. The dinosaur dynasty was no different. Beyond the raw power of their teeth and armor, we find compelling evidence of complex behaviors and sophisticated tactics that challenge the outdated notion of dinosaurs as simple, brutish beasts. A prime case study in this reevaluation is the velociraptor. Due to its portrayal in popular culture, this creature has been mythologized into a large, terrifying, scaly monster. The scientific reality, however, is both different and far more fascinating from a strategic perspective. The true velociraptor, discovered in the fossil beds of Mongolia, was a significantly smaller operative, roughly the size of a modern turkey and weighing perhaps 15 to 20 pounds. Far from being scaly, it was covered in a complex coat of feathers, a fact confirmed by the presence of quill knobs on its forearm bones, the same structures that anchor flight feathers in modern birds. This revised profile does not diminish its effectiveness as a predator, it enhances it. Its small size would have granted it immense agility and stealth, allowing it to navigate dense undergrowth and exploit niches unavailable to larger carnivores. But do not let its size fool you. The velociraptor was an agile and intelligent predator armed with a lethally specialized weapon, a large sickle-shaped claw on each foot. This talon was held retracted while walking to keep it razor-sharp and could be deployed with deadly precision to slash and pin prey. Fossil evidence provides a stunning frozen tableau of this capability. A specimen of velociraptor locked in mortal combat with a protoceratops, its killing claw embedded in the herbivore's neck region. This was not a mindless brute. This was a high-precision instrument of predation. The strategic implications deepened when we consider the evidence for coordinated action. One of the most compelling and chilling theories about raptors is that they may have operated as a cohesive unit, employing pack-hunting tactics similar to modern wolves or lions. Fossil sites containing the remains of multiple raptor-like dinosaurs that died together suggest group behavior. While a single raptor was dangerous, a coordinated pack would have been a force multiplier, capable of overwhelming much larger and more powerful prey through flanking maneuvers, distraction, and focused simultaneous attacks. Imagine a squad of these swift feathered hunters fanning out across a clearing, using silent signals to drive their target into an ambush. This leap from individual hunter to coordinated unit represents a significant cognitive and social advancement. It is proof that in the prehistoric world, intelligence and teamwork were every bit as important as they are on the battlefields of today. This level of social complexity was not limited to predators. Among the herbivores, we find evidence of one of the most sophisticated communication systems in the animal kingdom. The elaborate hollow crests of certain hadrosaurs, such as the famous Parasaurolophus, were more than just visual ornaments. They were acoustic instruments. These crests, some stretching up to 6 feet in length, were filled with a complex network of air passages connected to the nasal cavity. Scientists believe these structures functioned as resonating chambers, allowing the dinosaurs to produce deep, haunting, low-frequency calls that could carry for miles across the landscape. Computer models based on the internal structure of these crests suggest the tones were powerful and resonant, closer to a trombone or a French horn than a simple bird call. This was a long-range communication network. These calls were likely used to maintain herd cohesion over vast distances, warn of approaching predators, attract mates, or signal social status. Imagine a herd of hadrosaurs grazing at dusk as one lifts its head to broadcast a low, vibrating call that echoes across the floodplain, a call that is answered by others in a complex prehistoric chorus. This discovery adds an entirely new sensory dimension to their world, revealing it as a place not just of sight and motion, but of complex coded sounds. A world of information warfare where survival could depend on hearing a signal before the threat arrived. For generations, the collective human imagination painted the world of the dinosaurs in a muted, monotonous palette. They were envisioned as sluggish, scaly reptiles, their hides rough, leathery, and rendered in dull shades of gray, green, and brown. This image, reinforced by a century of museum exhibits and popular art, was not just an aesthetic choice. It was a reflection of the prevailing scientific dogma that dinosaurs were little more than oversized lizards. But in the late 20th and early 21st centuries, a series of stunning fossil discoveries, primarily from the Liaoning province in China, triggered a paradigm shift so profound it shattered the old orthodoxy. These fossil beds, which preserved ancient ecosystems with exquisite Pompeii-like detail, provided the smoking gun. Many species of dinosaurs, especially the theropod lineage from which predators like Tyrannosaurus rex arose, were covered in feathers. This was not a minor revision to the textbook, it was a revolution. The evidence was undeniable. Slabs of stone revealed dinosaur skeletons surrounded by a clear halo of preserved plumage. These were not the simple downy tufts of a hatchling bird. The fossil record showed a full spectrum of feather evolution, from primitive hair-like filaments to complex veined feathers nearly identical to those of modern birds. This discovery forced a complete recalibration of our understanding of dinosaur biology and appearance. Imagine a velociraptor not as a green, scaly creature, but as a dynamic, bird-like hunter with a sleek coat of feathers, perhaps even complex wings on its arms, darting through the undergrowth. These feathers may have initially evolved for insulation, a critical adaptation for the active, warm-blooded metabolism that we now believe many dinosaurs possessed. They could have also been used for dramatic social signaling, to attract mates, or to intimidate rivals. This revelation transforms our entire vision of the prehistoric world, replacing the drab reptilian landscape with a far more vibrant, dynamic, and bird-like reality. The revolution did not stop with the discovery of the feathers themselves. An even more astonishing breakthrough in paleoforensics allowed scientists to resurrect the lost colors of the Mesozoic. For years, the actual coloration of dinosaurs was considered unknowable, a detail lost forever to the ravages of deep time. But scientists discovered that within some exceptionally preserved fossilized feathers, microscopic structures called melanosomes remained intact. In living animals, these tiny organelles contain pigments, and their specific shape and arrangement determine the color of skin, scales, and feathers. By analyzing these fossilized melanosomes with powerful scanning electron microscopes and comparing them to the melanosomes of modern birds, researchers could decode the colors of creatures that died over 100 million years ago. The results were breathtaking. The evidence revealed that dinosaurs came in a dazzling array of hues and patterns. Some were matte black, others deep auburn red, and some possessed an iridescent quality, their feathers structured to refract light, creating a shimmering metallic sheen like that of a modern hummingbird or starling. Imagine a small dinosaur perched on a fern, its plumage catching the filtered sunlight in brilliant flashes of green, violet, and gold. These dazzling displays were not random. They were a critical part of their survival strategy. They were signals used in the high-stakes game of mate selection, territorial disputes, and species recognition. They reveal a prehistoric world that was not a dull gray land of lumbering beasts, but a place filled with vibrant spectacle and flashes of brilliant color. When we look at a peacock fanning its tail or a magpie showing off its iridescent sheen, we are witnessing the echoes of a visual language that was first spoken by the spectacular feathered dinosaurs that once ruled the Earth's forests and plains. In a natural male narrator, power is ultimately projected and maintained by the capabilities of its most advanced weapon systems. In the late Cretaceous period, the undisputed apex predator, the ultimate expression of terrestrial carnivorous evolution, was the Tyrannosaurus rex. Few creatures in the planet's history inspire such a primal sense of awe and terror. Its reputation is not a product of modern myth-making. It is a conclusion based on the cold, hard data written in its fossilized bones. The primary weapon system of the T-Rex was its skull and jaws. a marvel of biomechanical engineering designed for a single, brutal purpose: to generate and deliver the most powerful bite force of any land animal that has ever lived. Scientific models based on the architecture of its skull and the immense attachment points for its jaw muscles indicate a bite force that could reach an unimaginable 12,000 pounds of pressure. To put this number in perspective, it is the equivalent of the full weight of an adult elephant concentrating on a single point. This force was sufficient to crush the bones of its prey clean through, turning armored herbivores into splintered fragments in a matter of seconds. An examination of its dental array reveals that its teeth were not the delicate slashing knives of many other predators. Instead, they were thick, serrated, and shaped like bananas, some growing up to a foot long, including the root. This design was not for slicing flesh, but for gripping, puncturing, and transferring the full catastrophic force of the jaw muscles. They were, in essence, biological armor-piercing rounds. When a T-Rex bit down, there was no defense, no escape. Bone, muscle, and even the formidable armor of creatures like Triceratops all shattered beneath its power. Fossilized T-Rex dung, or coprolites, have been found containing the pulverized bone fragments of its victims, a testament to a digestive system that processed the evidence of the kill. And yet, for all its brute force, the T-Rex was not a simple killing machine. Fossil evidence, including its large olfactory bulbs, suggests it had a highly developed sense of smell, allowing it to track prey over vast distances. There is ongoing scientific debate about its operational doctrine. Was it a pure apex predator, actively hunting its prey, or was it also an opportunist, a strategic scavenger that used its size and power to intimidate other predators and steal their kills? The answer is likely both. Like most modern carnivores, it would have been adaptable, hunting when necessary and scavenging when the opportunity arose. Whatever the case, its jaw remains the ultimate symbol of predatory dominance, a kinetic weapon of such finality that it has no parallel on land, past, or present. It was the logical endpoint of the Mesozoic arms race, a predator perfectly evolved to defeat the most advanced defenses that evolution could produce. It is this image of high-performance predation that makes the diversity of dinosaur evolution so utterly compelling. The T-Rex represents a strategy of success through immense power, sophisticated sensory input, and lethal force. But this was not the only path. To understand the sheer breadth of what was possible, we must contrast this apex predator with another highly successful yet fundamentally different creature, the Stegosaurus. As we analyzed its defensive weaponry earlier, we must now confront its most startling feature, its brain, which was no larger than a walnut. Here we have a multi-ton animal, a walking fortress armed with plates and deadly spikes that operated with a central processing unit of shockingly limited capacity. This animal thrived for millions of years, not through cleverness or tactical thinking, but through a doctrine of passive, impregnable defense. The contrast is a profound lesson in evolutionary strategy. The T-Rex was a sophisticated, high-tech weapon. The Stegosaurus was a simple, brutally effective shield. Both were immensely successful. Their divergent paths remind us that survival in the ancient world was not a matter of following a single blueprint, but of finding a specialized strategy that worked, proving that in the long run of evolution, there is more than one way to win. The long-term success of any dynasty rests not on the power of a single generation, but on its ability to project that power into the future. For the dinosaurs, this meant mastering the complex strategic challenge of reproduction. The fossil record provides a remarkably intimate window into this process, revealing a world of fragile beginnings, immense vulnerability, and divergent strategies for ensuring the survival of the next generation. The primary evidence comes from one of the most delicate and revealing types of fossils, the dinosaur egg. And just as adult dinosaurs spanned a breathtaking range of sizes, so too did the vessels from which they began their lives. At one end of the spectrum, we find treasures of immense fragility. Fossilized eggs attributed to tiny theropods reveal shells no larger than a marble, smaller than the eggs laid by many modern quail. These miniature time capsules remind us that the dinosaur dynasty was not composed solely of titans. It included a vast ecosystem of smaller creatures whose life cycles were rapid and precarious. Imagine a nest, carefully tucked into soft earth and lined with vegetation, holding a clutch of these tiny speckled eggs. From them would hatch feathered young no bigger than a human hand, their survival utterly uncertain in a world dominated by giants and patrolled by a host of predators. The existence of these tiny eggs underscores the incredible vulnerability that lay at the heart of the dinosaurian life cycle. Fossils sometimes preserve these scenes with haunting clarity, freezing entire nests in stone with the delicate bones of embryos still curled inside. Each tiny egg is a self-contained story from millions of years ago, a testament to the fact that even the most powerful and successful creatures on Earth began their journey in something small, delicate, and astonishingly fragile. On the opposite end of the reproductive scale, we find a strategy of industrial magnitude. The eggs of the giant sauropods, the titans of the Mesozoic, reached extraordinary sizes, with some measuring more than a foot in length, easily larger than a modern basketball. Imagine stumbling across a vast nesting ground, a prehistoric nursery, with hundreds of these enormous half-buried shells stretching across the ancient sands. Each one of these massive eggs contained a creature destined to grow into a titan, an animal that would eventually stretch more than 100 feet long. Yet even these giant eggs were infinitesimally small compared to the colossal adults they would one day become. The sheer disparity in size between hatchling and adult presented a unique strategic problem. The hatchlings were incredibly vulnerable for a long period of their lives. To counter this, the sauropods adopted a strategy of overwhelming numbers. Scientists believe they laid many eggs at once, likely in large communal nesting grounds, effectively playing a statistical game of survival. The overall mood of dinosaurs was that of cold, unfeeling reptiles that, like many modern lizards, abandoned their eggs after laying them. But a wealth of fossil evidence has completely overturned this assumption, revealing a world of complex social bonds, dedicated parental care, and coordinated group behavior. This evidence paints a tender and strategically sophisticated picture of prehistory, one in which even colossal creatures invested significant time and energy into nurturing their young. Far from being solitary monsters, many dinosaurs appear to have lived in complex family groups defined by care and cooperation. One of the most dramatic stories of this scientific reassessment is the redemption of a dinosaur known as Oviraptor. Its name, which means egg thief, was given in the early 20th century when the first fossil was discovered near a clutch of what were believed to be Protoceratops eggs. For decades, the oviraptor was vilified in textbooks and museum displays as a cowardly nest raider. But subsequent discoveries in the Mongolian desert revealed a stunning and poignant truth. New fossils were found showing oviraptor adults in a protective, bird-like brooding posture directly on top of these same types of nests. The eggs did not belong to another species, they were its own. The egg thief was, in fact, a devoted parent. Some of these fossils are truly heartbreaking, capturing parents that were buried alive by collapsing sand dunes, their arms spread wide to shield their nests from the storm, refusing to abandon their young even at the cost of their own lives. This evidence transformed Oviraptor from a villain into a profound symbol of parental care, a behavior that links them directly to their modern bird descendants. This strategy of extended nurturing is supported by other species as well. Fossil evidence from hadrosaur nesting sites suggests that their fragile, newly hatched babies remained in the nest for weeks or even months. An analysis of their tiny limb bones shows that they were not developed enough to support their weight or allow them to forage independently. This indicates that they were completely reliant on their parents for protection and sustenance. Imagine a vast nesting colony filled with the soft chirping of downy hatchlings, while attentive mothers and fathers guarded the perimeter and brought back vegetation to feed their growing offspring. This behavior represents a significant strategic investment. By guarding their young during this period of extreme vulnerability, parents dramatically increase the odds of their survival, ensuring a higher return on their reproductive efforts. This picture of a complex social world is further solidified by one of the most compelling forms of evidence: fossilized trackways. Sometimes the most revealing fossils are not bones, but the footprints left behind. Vast pathways of fossilized tracks found all over the world show dozens, sometimes even hundreds, of dinosaurs moving together in the same direction. These traces are undeniable proof that many species, including the giant sauropods and the duck-billed hadrosaurs, traveled in large, organized herds, much like modern elephants or wildebeest. These are not random collections of footprints, they are geospatial data that reveals social structure. The tracks often show a clear formation, with the largest footprints of adult animals on the outside of the group, while the smaller tracks of juveniles are clustered safely in the center. This is the blueprint of a coordinated defensive strategy, a living, moving shield designed to protect the next generation. These pathways tell us about social dynamics in a way that bones never could, revealing a world not of solitary wanderers, but of complex communities moving across ancient landscapes in dynamic, ever-shifting herds. The evidence of complex herds and social structures points to a dynasty capable of coordinated action on a vast scale. This capability was not limited to defense. It was essential for undertaking one of nature's most astonishing behaviors: mass seasonal migration. The dinosaurs were not static occupants of a single territory. Many species were masters of long-distance travel, undertaking epic journeys that spanned hundreds, perhaps even thousands of miles. This was not aimless wandering. It was a strategic imperative, a carefully orchestrated movement to follow shifting food sources and favorable climates across entire continents. The evidence for these migrations is etched into the geological record. Vast trackways, like those found in North America, hint at enormous herds of hadrosaurs moving seasonally, their combined footprints carving literal highways into the prehistoric landscape. But even more compelling evidence comes from sophisticated forensic analysis of their remains. Isotope studies of fossilized dinosaur teeth have provided a chemical roadmap of their lives. The specific isotopic signatures of elements like oxygen, found in the water and animal drinks, become locked into the enamel of its growing teeth. By analyzing these signatures layer by layer, scientists can determine the different geographical regions an animal inhabited throughout its life. This is a form of natural geotagging, and it confirms that these creatures traveled enormous distances, drinking from water sources that were hundreds of miles apart. Imagine the spectacle: vast, living rivers of dinosaurs marching across floodplains, mothers guiding their young, with apex predators shadowing the herds, all moving in rhythm with the ancient seasons. These seasonal migrations would have carried them through dramatically changing environments, from lush forests to open plains, a grand planetary-scale rotation that ensured their survival during harsh times, proving their mastery over not just a single ecosystem, but over the entire continent. The ultimate testament to the success of the dinosaurian dynasty, however, is written on the global map itself. Their fossils have been found on every single continent, from the plains of North America to the deserts of Asia, from the heart of Africa to the frozen wastes of Antarctica. They were truly global creatures, the first group of land animals to achieve complete planetary colonization. The overall mood of their reign in the Triassic and Jurassic periods, the Earth's continents were largely fused together into the supercontinent of Pangaea, which provided a land bridge for their initial global expansion. As Earth's tectonic plates began to drift apart, breaking up this massive landmass, dinosaur populations became isolated on new island continents. This geological separation was a primary driver of their incredible diversification, as isolated groups adapted to unique local environments, evolving into a spectacular array of new species. The discovery of their fossils in Antarctica is perhaps the most striking proof of their adaptability. It is a concept that is difficult to reconcile with our modern image of the southernmost continent as a desolate desert of ice and snow. But during the Age of Dinosaurs, Antarctica was a green and fertile world. It was located further north, and the global climate was significantly warmer. Fossilized wood from ancient trees, impressions of leaves, and the bones of multiple dinosaur species, including sauropods, theropods, and ornithods, reveal a land that was once covered in temperate forests and crisscrossed by rivers. The dinosaurs that lived in this polar environment had to be exceptionally resilient, adapted to a unique and extreme cycle of seasons. They would have experienced months of continuous 24-hour daylight during the summer, followed by months of unending darkness and cold during the winter. These polar dinosaurs stand as the ultimate symbol of the dynasty's resilience, demonstrating their ability to conquer not just the tropics, but the very edges of the habitable world. The dinosaurian conquest of Antarctica's polar seasons was not an isolated anomaly. It was part of a broader pattern of global colonization that saw them push into the most extreme environments the planet had to offer. Just as they thrived at the South Pole, so too did they conquer the far north. Fossil discoveries in Alaska, Siberia, and other Arctic regions have confirmed that dinosaurs once roamed near the North Pole. These were not seasonal tourists migrating north for a brief summer. Bone beds and trackways suggest that large herds of dinosaurs, particularly hadrosaurs, were year-round residents of these high-latitude environments. This presented them with an even more profound strategic challenge than just the cold: the polar night. For months on end, their world was plunged into a deep, unrelenting darkness, a condition that would have brought photosynthesis to a grinding halt and fundamentally reshaped the dynamics of the ecosystem. To survive in such an environment, these Arctic dinosaurs must have possessed a unique suite of advanced adaptations. Fossilized skulls from some of these species show unusually large eye sockets, leading paleontologists to hypothesize that they had keen night vision. Their eyes adapted to gather every last photon of light in the dim sub-zero twilight. Others may have relied on an enhanced sense of smell or hearing to navigate and find scarce vegetation in the dark. But their most critical asset would have been their warm-blooded physiology. Their ability to generate their own internal body heat, a key feature that separates them from cold-blooded reptiles, would have been essential to remain active and survive the freezing conditions. Imagine the scene: a herd of feathered herbivores moving slowly through a snow-dusted polar forest, lit only by the stars and the aurora, steam rising from their warm bodies into the frigid air. Their existence in this extreme frontier demonstrates the astonishing versatility of the dinosaur dynasty. They were not limited to the warm, tropical climates of popular imagination. They were resilient pioneers, capable of enduring and even flourishing at the very edges of Earth's habitable zones. Their relentless push into new frontiers was not limited to land. For a long time, dinosaurs were imagined as exclusively terrestrial creatures, awkward and out of place in the water. But one remarkable predator shattered that perception, proving that the dynasty was capable of launching an amphibious assault on the river systems of the Cretaceous. This creature was Spinosaurus. With its elongated crocodile-like snout, conical teeth perfect for gripping slippery prey, and a spectacular sail-like structure on its back, it was already one of the most unusual carnivores known. But recent fossil discoveries, including a remarkably complete tail, have confirmed a startling hypothesis. Spinosaurus was semi-aquatic and may have spent a significant portion of its life hunting in the water. Its anatomy represents a radical departure from the typical land-based predator blueprint. Its bones were unusually dense, a feature that would have reduced its buoyancy and helped it control its position in the water column, much like the ballast in a submarine. Its powerful paddle-like tail, propelled by massive muscles, would have allowed it to move through the water with lethal speed and efficiency. Imagine a predator longer than a Tyrannosaurus rex gliding silently beneath the surface of a vast river system, a reptilian crocodile of immense proportions, waiting to ambush giant fish or any land dweller foolish enough to come too close to the water's edge. Spinosaurus represents a remarkable evolutionary pivot, a dinosaur that successfully conquered a niche we once thought was impossible for them. It may have been the first truly aquatic non-avian dinosaur, a lord of both the riverbanks and the watery depths, proving that the dynasty's innovative spirit was so powerful that it pushed them to conquer not just the land but the water as well. The Dinosaurian dynasty's mastery of the planet's land and its successful push into its waterways represents a staggering level of ecological dominance. But there was one final frontier to conquer: the sky. Here, we must address a critical distinction, a common misconception that clouds the true strategic picture of the Mesozoic. The flying reptiles that patrolled the ancient skies, the pterosaurs, were not dinosaurs. Though they lived alongside them for over 150 million years and shared a common ancestor deep in their evolutionary past, they belonged to a distinct and separate branch of the reptile family tree. They were a sister dynasty, an allied power that established an undisputed air superiority that lasted for the entire duration of the dinosaurs' reign. To understand this era, one must see it as a world controlled by two dominant empires, the dinosaurs ruling the land and the pterosaurs commanding the air. Before the evolution of true powered flight, however, some smaller feathered dinosaurs engaged in their own experiments to leave the ground. These were not the masters of the sky, but the stealthy operatives of the forest canopy. Fossils of creatures such as Microraptor and the bizarre Yi-Chi reveal creatures that evolved the ability to glide. With feathered limbs spread wide to catch air currents, or, in the case of Yi-Chi, elongated fingers supporting a bat-like membranous wing, these animals could drift gracefully from branch to branch. This was not true flight, but a controlled fall, a way to navigate the three-dimensional battlefield of the forest with unparalleled efficiency, ambushing prey from above or escaping terrestrial predators. These were the glider infantry of the Mesozoic, a fascinating evolutionary side branch that illustrates the relentless pressure to become airborne. But it was the pterosaurs that achieved the ultimate prize: true powered flight. They were the first vertebrates in the planet's history to do so, predating birds and bats by tens of millions of years. Their command of the air was total and absolute. This dynasty of flyers was just as diverse and varied as their terrestrial cousins, evolving a spectacular array of different aerial platforms. Their wingspans ranged from the size of a modern sparrow to the scale of a fighter jet. Smaller pterosaurs, with their agile wings and sharp beaks, would have flitted through forests like bats, hunting insects in the twilight.
Others were specialized marine hunters, skimming low over the oceans to snatch fish from the surface. Their fossils found in ancient seabeds far from any land. And then there were the giants. The late Cretaceous pterosaurs, such as the colossal Quetzalcoatlus, were the largest flying animals that have ever existed. With a wingspan of over 30 feet, they were as wide as a modern F-16 fighter jet. These were the strategic bombers of the ancient world. They soared on thermal updrafts, covering vast distances with minimal effort, their immense shadows passing over the herds of dinosaurs below. On the ground, they walked on all fours, stalking smaller dinosaurs and other prey with their long spear-like jaws. Their reign in the skies was a staggering success story. For 150 million years, they faced no serious aerial competitors. They were part of the same grand global stage as the dinosaurs, filling the skies while the dinosaurs ruled the land. Together, they created a world where power was projected across every dimension, a planet alive with the thunderous footsteps of giants on the ground and the silent, massive wing beats of titans in the air. The story of the Dinosaurian dynasty is not just a story of animals. It is inextricably linked to the story of the world they inhabited, a planet undergoing its own profound transformations. For the first two-thirds of their reign, the dinosaurs walked through a world that would seem alien to us, a landscape dominated by a hardy, ancient guard of vegetation. The global flora consisted primarily of ferns, ginkgos, conifers, and cycads, a relatively static, monotonous green kingdom. But around the mid-Cretaceous period, a botanical revolution began, a disruptive event that would permanently reshape the planet's ecosystems and alter the course of life itself. This was the rise of the angiosperms, the flowering plants. This was not a subtle change. It was a paradigm shift in the business of life. Before the angiosperms, plant reproduction was a far less efficient process, relying heavily on wind to carry pollen and spores. But flowers were a revolutionary new technology. They were sophisticated marketing devices, using vibrant colors, intricate patterns, and alluring scents to attract animal pollinators, primarily insects at first. This created a new, highly efficient and targeted system for gene transmission. Furthermore, these plants developed another brilliant innovation: fruit. By encasing their seeds in nutritious, fleshy packages, they co-opted animals into becoming their dispersal agents. This new business model, based on a co-evolutionary partnership with the animal kingdom, gave the angiosperms a decisive competitive advantage, and they began a campaign of global conquest. The dinosaurs were the incumbents, the ruling dynasty presiding over this botanical upheaval. They walked through forests that were slowly, then rapidly blooming, a world filling with colors and scents never before experienced on Earth. This new resource base would have had a profound impact on the herbivorous dinosaurs. The rise of fast-growing, highly nutritious flowering plants may have been a key driver in the evolution of some of the most advanced herbivores of the late Cretaceous. Creatures like the hadrosaurs, with their sophisticated dental batteries capable of grinding tough new vegetation, were perfectly adapted to exploit this changing food supply. The relationship was likely reciprocal. While we often think of bees and butterflies as pollinators, it is plausible that some small, feathered dinosaurs or primitive birds played a role in this new economy, carrying pollen from blossom to blossom as they searched for nectar or insects. Larger herbivores, by consuming fruits and then traveling vast distances, would have acted as highly effective long-range seed dispersers. Imagine a herd of triceratops grazing among cycads but also plucking at bright, fragrant flowers, unwittingly participating in the spread of the very plants that were transforming their world. By the end of the Cretaceous, the revolution was complete. What began as a quiet insurgency in the undergrowth had become a total victory. Flowering plants had come to dominate most terrestrial ecosystems. The world of the last dinosaurs, the world of Tyrannosaurus rex and Triceratops, was not the stark, primeval landscape of their Jurassic ancestors. It was a world of flowers, fruits, and buzzing insects, a world that in many ways was beginning to resemble our own. This botanical transformation reshaped entire food chains, laying the foundation for modern ecosystems long before the mammals rose to prominence.
The dinosaurs were there to witness the first gardens the Earth ever produced. Unknowingly, they were living through a profound alteration of their global resource base, adapting to a flowering world that was paving the way for the age that would follow their own. The overall mood of a natural dynasty extended beyond their direct interactions with the flora and fauna of their time. Their sheer scale, their immense numbers, and their unique physiology meant that they had a profound, unintended, and planet-altering impact on the very atmosphere of the Earth. We have analyzed their physical presence, the seismic shock of their footsteps, and their role as gardeners of a new flowering world. But now we must examine their invisible legacy, the chemical footprint they left on the sky. A compelling and startling scientific hypothesis suggests that the dinosaurs, particularly the giant sauropods, were a significant force in shaping the global climate through the massive quantities of methane they produced. It is a concept that sounds almost humorous, yet it is based on sound biological and climatological principles. Methane is a potent greenhouse gas, far more effective at trapping heat in the atmosphere than carbon dioxide. In the modern world, ruminant animals like cows are a significant source of atmospheric methane, produced as a byproduct of the gut bacteria that help them break down tough, fibrous vegetation. Now extrapolate that principle to the Mesozoic. Imagine not a herd of cows, but a herd of Argentinosaurus, each weighing over 70 tons and consuming vast quantities of plant matter every single day. Their digestive systems would have functioned as colossal, mobile bioreactors, relying on methanogenic microbes to process their food. The amount of methane released as a byproduct would have been enormous. Scientists have attempted to model the potential output, and the numbers are staggering. Global emissions from sauropod herds may have amounted to hundreds of millions of tons per year, a figure that could have had a direct and measurable impact on the planet's climate. The overall mood of a warm, friendly conditions that characterized much of the Mesozoic era. In essence, the dinosaurs may have been a crucial component of a massive climate feedback loop. The warm, carbon-rich atmosphere encouraged rampant plant growth, providing an abundant food source for the enormous sauropods. In turn, the sauropods processed this vegetation and released immense volumes of methane, which further trapped heat in the atmosphere, helping to sustain the very climate that allowed their food source to flourish. This theory transforms our understanding of these creatures. They were not merely passive inhabitants of their environment, they were active participants in its creation. They were a biological force of nature on a geological scale. Imagine entire herds grazing across a vast floodplain, their collective digestive processes subtly but relentlessly altering the chemical composition of the air around them. This humbling idea highlights the profound and often unexpected ways that life can influence global systems. It provides a deep-time perspective on our modern climate concerns, demonstrating that the planet's atmosphere has always been in a delicate dance with the dominant life forms that call it home. The dinosaurs remind us that a dynasty's power is not just measured in its physical might, but in its ability to fundamentally reshape the world right down to the air itself, through the simple, collective act of living. To reconstruct the intricate workings of the lost dinosaurian world, scientists must become detectives, piecing together a complex puzzle from fragmentary clues. While skeletons provide the architectural blueprint of these creatures, it is the rare and often overlooked trace fossils that provide a visceral, high-resolution snapshot of their daily lives. A natural male narrator, uncover fossils that hold more than just bone. They contain the preserved remnants of a dinosaur's last meal, a final, intimate record of survival frozen for millions of years. These discoveries are the equivalent of a forensic report from the deep past, offering direct, irrefutable evidence of the intricate food web that defined the Mesozoic. These gastric time capsules give us an unfiltered look into the reality of their existence. Some herbivore fossils have been found with partially digested plants still within their abdominal cavities, revealing the specific types of ferns, cycads, or flowers that grew in prehistoric forests. In predators, the evidence is often more dramatic. The fossilized remains of the small theropod Compsognathus were famously found with the skeleton of a small lizard inside, a perfect record of its final hunt. Another fossil, a microraptor, contained the remains of a small primitive bird, proving its predatory habits in vivid detail. These finds are invaluable because they move beyond the realm of inference. We can analyze a predator's teeth and hypothesize about its diet, but these stomach stones of time prove not just what dinosaurs could eat, but what they actually did eat in the final moments of their lives. It's humbling to realize that the remains of a single meal can endure for tens of millions of years, telling a story of what life was like on an ordinary day in a world long vanished. Just as crucial, though perhaps less glamorous, is the study of what came after the meal. Fossilized dinosaur dung, known to science as coprolites, is one of the most fascinating and data-rich types of fossils. These ancient droppings, hardened and mineralized over eons, preserve not just waste, but microscopic fragments of what the dinosaurs consumed. Seeds, bone fragments, fish scales, and plant fibers often remain locked inside, turning a piece of dung into a prehistoric diary of an animal's diet and its local ecosystem. By placing a coprolite under a microscope, scientists can reconstruct the structure of local food chains, identify what kinds of plants were dominant in a specific region, and even analyze the efficiency of different digestive systems. Some of these coprolites are monumental. Among the largest ever discovered is a specimen from the late Cretaceous of Saskatchewan, weighing over 40 pounds, heavier than a cinder block. It is believed to have been produced by a massive predator, almost certainly a Tyrannosaurus rex. When scientists analyzed this colossal coprolite, they found it was densely packed with the crushed bone fragments of a juvenile herbivore. This discovery is astonishing. It offers direct physical confirmation of the T-Rex's bone-crushing feeding strategy, proving that it consumed and processed huge quantities of its prey, bones and all. It is a visceral and powerful piece of evidence, a goldmine of information that tells us about the predator's metabolism and the sheer volume of food required to power its multi-ton body. The study of coprolites is a potent reminder that in the grand investigation into the past, no trace of life is too humble to matter. Even waste becomes a treasure when it holds the secrets of a vanished world. The relentless search for energy to power their colossal bodies forced the great herbivorous dinosaurs to solve a fundamental engineering problem: how to efficiently break down enormous quantities of tough, fibrous plant matter.
As we have seen, the hadrosaurs evolved a high-tech solution in the form of their sophisticated dental batteries. But other lineages, particularly the giant sauropods, adopted a different yet equally ingenious low-tech strategy.
These giants, with their simple, peg-like teeth designed for raking and stripping leaves, did not chew their food in their mouths. Instead, they outsourced the grinding process to a powerful internal machine. They swallowed stones. This was not an accidental behavior. Certain dinosaurs would intentionally gulp down smooth stones, which are known to science as gastroliths, from the Greek for stomach stones. These rocks would travel down the esophagus and settle in a specialized muscular part of the stomach, likely similar to the gizzard found in modern birds and crocodiles. This organ would then contract powerfully, tumbling the stones around with the swallowed vegetation, pulverizing the tough plant fibers before they moved deeper into the digestive tract. In essence, the dinosaurs had created a biological stone tumbler, an internal ball mill that performed the function of chewing long after the food had been swallowed. This simple, elegant solution allowed them to process immense volumes of coarse material that would have otherwise been indigestible. The forensic evidence for this behavior is both compelling and unambiguous. Paleontologists have discovered the skeletons of sauropods and other herbivores with distinct clusters of highly polished, rounded stones nestled within their rib cages, precisely where the gizzard would have been located. These are not random rocks that were buried with the animal. Their smooth, worn surfaces are the result of constant grinding against each other and against fibrous plant matter over the course of the animal's life. Furthermore, these gastroliths are often composed of rock types that are geologically alien to the sedimentary layers in which the dinosaur fossil was found. This is the smoking gun, proving that the dinosaur swallowed these stones in one location and carried them for potentially hundreds of miles throughout its migratory life. A portable, self-contained food processing unit.
This remarkable adaptation provides yet another powerful, direct link between the dinosaurs and their living descendants. Many modern birds, from chickens swallowing grit to ostriches gulping down pebbles, still employ this exact same strategy. It is an ancient technology, a testament to an evolutionary solution so effective that it has persisted for over 150 million years. The humble gastrolith, a simple stone that once rolled along a Jurassic riverbed, became a vital component in the digestive machinery of the largest animals ever to walk the earth. It is a profound example of how evolution often finds clever, robust solutions using the simplest tools available, turning the very rocks of the landscape into an essential gear in the engine of life. Having explored the internal, often microscopic, evidence of the dinosaurs' lives, we now return our focus to the outside, to the breathtaking and often logic-defying scale of their anatomy. Among the sauropods, the long-necked giants, evolution produced biological structures of such staggering length and complexity that they challenge the very limits of biomechanical engineering. Some of these necks stretched for over 30 feet, a length greater than the entire body of a modern giraffe. This was not simply an elongated feature, it was a sophisticated, high-performance feeding apparatus that allowed these giants to exploit resources far beyond the reach of any competitor. The engineering challenges involved in creating and operating such a structure are extraordinary. The neck had to be strong enough to support its own immense weight, flexible enough to navigate through dense forests, and stable enough to serve as a precise tool for stripping leaves from branches. The secret to this evolutionary marvel lies in the vertebrae themselves.
While a mammal, like a human, has only 7 neck vertebrae, many sauropods had 15 or more, each one an intricate, lightweight masterpiece. The bones were not solid. They were highly pneumatized, meaning they were filled with a complex system of air sacs connected to the respiratory system. This design, similar to the bones of modern birds, was the critical innovation that made such colossal necks possible. It dramatically reduced their weight without sacrificing their structural integrity, creating a biological equivalent to the hollow trusses of a modern bridge or crane. But even with this weight-saving measure, the physiological demands were immense. The heart of a large sauropod would have had to work as a phenomenally powerful pump, generating incredible blood pressure to drive oxygenated blood stories high to a brain perched at the end of that colossal neck. Furthermore, not all sauropods utilized this technology in the same way. The dynasty produced divergent strategic models for this unique piece of hardware. Some species, like the famous Diplodocus, appear to have held their necks out horizontally, sweeping them from side to side across the landscape like a colossal vacuum hose. This posture would have allowed them to efficiently clear vast swaths of low-lying ferns and shrubs without having to move their multi-ton bodies, a crucial strategy for conserving energy. In stark contrast, the iconic Brachiosaurus was engineered as a living skyscraper. Uniquely among sauropods, its front legs were significantly longer than its back legs, tilting its entire body upward. This posture, combined with its immense neck, transformed the Brachiosaurus into a mobile feeding tower, a biological cherry picker capable of reaching the tops of the tallest prehistoric trees, a feeding niche it would have had almost entirely to itself. Standing as tall as a 5-story building, the Brachiosaurus was one of the most breathtaking creatures of the Mesozoic. To stand beside one would have been like standing at the foot of a living, breathing building that could walk. The high placement of its nostrils on the top of its head once led scientists to believe it was an aquatic creature that used them as a snorkel, a theory now largely discredited. The true function remains an intriguing mystery, perhaps related to vocal resonance or display. But its very existence, a creature built on a scale that defies our modern experience, is a testament to the power of evolution to solve the most extreme engineering challenges, pushing the boundaries of flesh and bone to create a creature that was, in every sense of the word, monumental. While the mainstream evolutionary paths of the dinosaur dynasty produced dominant models like the colossal sauropods and the heavily armored ankylosaurs, a host of side branches and experiments produced some of the most bizarre and specialized creatures ever to walk the Earth. These were not failed prototypes. They were highly successful specialists, each with a unique and often strange arsenal of anatomical tools adapted for a specific way of life. They are a testament to evolution's relentless creativity, its willingness to tinker with the standard blueprint to produce novel solutions to the timeless problems of survival and reproduction. Consider the early Jurassic predator, Dilophosaurus. This creature was distinguished by the pair of thin, delicate plate-like crests that grew from the top of its skull. These structures were likely far too fragile for use in physical combat, leading scientists to conclude that their primary function was for display. The overall mood, perhaps flushed with vibrant colors, acting as a billboard to signal health, maturity, or social status to rivals and potential mates. Dilophosaurus was one of the largest predators of its time, a 20-foot-long carnivore that relied on powerful jaws and agility. Its pop culture portrayal as a small, frilled, venom-spitting creature is pure cinematic fiction. There is absolutely no fossil evidence to support either a neck frill or a venom-spitting capability. The real animal was far larger and more impressive, a predator that balanced its lethality with an elegant and sophisticated system of visual communication, a showpiece of evolution.
Another predator that represents a strange evolutionary trade-off was the Carnotaurus. Its name means meat-eating bull, a reference to the two sharp horns that projected from its skull just above its eyes. While its body was sleek and built for speed, its most confounding feature was its arms. They were almost comically small, even more reduced than those of Tyrannosaurus rex, to the point of being almost entirely useless. The joints were stiff, limiting their range of motion, and the hands were tiny. While T-Rex's arms were short but heavily muscled, the arms of Carnotaurus appear to have been true evolutionary leftovers, appendages that were sacrificed as other traits, like its powerful legs and skull, became more important. This creature was a formidable and efficient predator, but its anatomy is a stark lesson in evolutionary priorities, a puzzle that shows how sometimes success is achieved by giving up on one feature to double down on another. Perhaps the most extreme example of cranial specialization can be found in the Pachycephalosaurs, the dome-headed dinosaurs. The tops of their skulls were formed into a massive, thickened helmet of solid bone, in some species growing to be more than 10 inches thick.
This biological battering ram was often adorned with additional knobs and spikes, turning the animal's entire head into a fearsome club. For decades, scientists have debated the purpose of this incredible structure. The leading theory, supported by fossil evidence of healed fractures and lesions on these domes, is that they were used in ritualized high-impact contests between members of the same species. Much like modern bighorn sheep or musk oxen, males likely battled for dominance, territory, or mating rights. Imagine two pachycephalosaurs charging across a clearing, their domes colliding with a thunderous, bone-shaking crack that would have echoed through the prehistoric forests. The incredibly thick bone was designed to absorb and dissipate these catastrophic impact forces, protecting their small brains while delivering a dramatic and decisive display of strength. These living battering rams remind us that in the evolutionary arms race, even the skull itself can be weaponized. The specialized arsenals of the dinosaur world were not limited to defensive or display structures. They found their ultimate expression in the lethal weaponry of the carnivores. While some predators relied on size and brute force, others evolved to become masters of high-precision combat. The raptors, a group of small to medium-sized intelligent predators, carried one of the most iconic and efficient killing tools of the entire Mesozoic era, a sickle-shaped claw on each of their hind feet. This was not just another talon, it was a specialized, retractable weapon. The claw, which could be several inches long, was held up off the ground as the animal walked, a sophisticated mechanism that protected its razor-sharp edge from becoming dull. When the raptor attacked, it could swing this claw down with devastating speed and precision. Microscopic analysis of these fossilized claws reveals edges that, when new, would have been sharper than a modern steak knife, capable of slicing through flesh with surgical ease. The exact combat application of this claw is a matter of intense scientific study. Some paleontologists believe it was used as a slashing weapon, with the raptor leaping and kicking to inflict deep, bleeding wounds that would quickly incapacitate its prey. Another compelling theory suggests it was used as a grappling tool, a biological grappling hook, to latch on to a struggling victim, pinning it to the ground while the raptor's jaws and hand claws delivered the final blows. Either way, it was a devastatingly effective weapon that, when combined with their intelligence, agility, and possible pack hunting behavior, turned these relatively small dinosaurs into some of the most formidable hunters in their ecosystems. The sickle claw is a masterpiece of evolutionary engineering, a perfect balance of form and function that proves that in combat, precision can be just as deadly as power. For decades, however, the story of the apex predator was dominated by a single name, Tyrannosaurus rex. It was crowned the undisputed king, the largest and most powerful terrestrial carnivore ever to have lived. But in the 1990s, discoveries from the ancient plains of South America revealed a challenger to the throne. A new predator was unearthed, one that was not only a contemporary of the giant sauropods, but was potentially even larger than T-Rex. Its name was Giganotosaurus. Stretching over 40 feet long, with a skull that measured more than 5 feet, this massive carnivore proved that the evolution of giant predators was not a one-time event limited to North America. What makes Giganotosaurus so fascinating is not just its size, but its different combat doctrine.
While Tyrannosaurus rex was a bone crusher built to end a fight with a single catastrophic armor-piercing bite, Giganotosaurus was a flesh slicer. Its skull, though massive, was more slender than a T-Rex's, and its teeth were not thick, bone-splintering spikes. Instead, they were long, narrow, and serrated like steak knives, designed to shear through flesh and inflict massive bleeding wounds. This suggests a completely different hunting strategy. It likely preyed upon the colossal Titanosaurus like Argentinosaurus, creatures so immense that a bone-crushing bite might not have been effective. The strategy of Giganotosaurus was likely one of attrition. It would use its powerful bite to carve huge chunks of flesh from the giant herbivore, causing immense blood loss and shock. It would then follow its wounded victim, waiting for it to weaken and collapse. This distinction represents two divergent paths in apex predator evolution. T-Rex, the heavyweight brawler delivering a knockout punch, versus Giganotosaurus, the relentless hunter armed with blades, bleeding its titanic prey to death. Its discovery proved that the title of King of the Dinosaurs was very much a regional one. For the entirety of their 160 million-year reign, the dinosaurs were the undisputed masters of the global ecosystem. They were the architects of their world, the titans of the land, the apex predators, and the colossal herbivores. But they did not rule alone. Living alongside them, often literally under their feet, was another group of animals, a lineage of survivors playing a very different, very long game. While the dinosaurs dominated the daylight world, a secret nocturnal world belonged to our own ancestors, the early mammals. For over 150 million years, these two dynasties coexisted on the same planet, one in the brilliant spotlight of ecological dominance, the other in the deep shadows of the undergrowth.
The mammals of the Mesozoic were, for the most part, nothing like the megafauna of today. They were generally small, often no larger than a modern shrew or rat, and lived lives of stealth and caution. By adopting a nocturnal lifestyle, they largely avoided direct competition with the dinosaurs. While the giants slept, these small, furry creatures scurried through the prehistoric night, hunting insects, worms, and perhaps scavenging the leftovers from a dinosaur's kill. They hid in burrows, nested in hollow logs, and developed keen senses of hearing and smell to navigate a world where a single misstep could mean being crushed by a passing giant. For tens of millions of years, this was the strategy of the mammalian lineage: stay small, stay hidden, and survive. They were the resilient underclass of an empire of giants, quietly persisting, adapting, and diversifying in the margins, setting the evolutionary stage for the world that was to come. This simple narrative of giant dinosaurs and cowering mammals, however, was dramatically complicated by a stunning fossil discovery that turned the entire predator-prey relationship on its head. In China, paleontologists unearthed the fossil of a badger-sized mammal called Repenomamus. This creature was one of the largest mammals of its time, a bold and successful animal.
But the truly shocking discovery was found within its fossilized ribcage, the unmistakable bones of a baby psittacosaurus, a small horned dinosaur. This was not a case of scavenging. The position of the bones indicated that the mammal had consumed the young dinosaur in one of its final meals. The hunter had become the hunted. This single fossil is a profound revelation. It shatters the simplistic idea that mammals were merely passive victims. It proves that the relationship between the two dynasties was far more complex and dynamic. Some mammals, at least, were bold and capable enough to prey upon the young of the ruling class. This discovery paints a vivid picture of the Mesozoic food web. For all their size and power, the dinosaurs were not invincible. Their dynasty was at its most vulnerable at the very beginning of the life cycle. Nests, eggs, and hatchlings were a tempting target for any opportunist, and a predator like Repenomus would have been a formidable threat to a young, defenseless dinosaur. This reversal of roles is a crucial reminder that even in an empire of giants, survival is a complex and brutal equation. The rulers of the earth had to contend with dangers from the most unexpected of places, from the small, intelligent, and hungry survivors that lived and hunted in their shadows. These mammals were biding their time, and in a dramatic twist of fate, the future of the planet belonged to them. For 160 million years, the Dinosaurian dynasty had endured every challenge the Earth could produce. They had survived continental drift, shifting climates, and a perpetual grinding arms race of evolution. Their global empire was resilient, adaptable, and seemingly eternal. On the final day of the Cretaceous period, the world was theirs. Herds of Triceratops moved through forests of flowering trees. A Tyrannosaurus rex surveyed its territory. And in the skies, the last of the giant pterosaurs soared on continental air currents. The dynasty was at its zenith, utterly unaware that its reign was about to be concluded, not by any terrestrial challenger, but by an executioner from the cosmos. The overall mood did not come gradually. It arrived in a single, catastrophic moment. Traveling through the void of space at a velocity of thousands of miles per hour was a 6-mile-wide asteroid, a remnant from the formation of our solar system. 66 million years ago, its orbital path intersected with that of Earth. It entered the atmosphere as a blinding fireball, a second sun that would have momentarily outshone the first. For the creatures on the ground, this would have been the last thing they ever saw. The asteroid struck a shallow sea in what is now the Yucatan Peninsula in modern-day Mexico. The site of the impact is known today as the Chicxulub crater. In an instant, an explosion of such magnitude was unleashed that it defies all human frames of reference. The energy released was equivalent to several billion atomic bombs detonating at the same moment. This was not a terrestrial event. It was a geological and atmospheric event on a planetary scale. At the moment of impact, the asteroid and the very crust of the Earth it struck were vaporized, creating a crater over 100 miles wide and miles deep. A superheated plume of molten rock, gas, and debris was blasted high into the atmosphere and beyond into the vacuum of space. On the ground, the immediate effects were apocalyptic. A thermal pulse, a wave of incandescent heat, radiated outwards from the impact site, incinerating all life for hundreds of miles. This was followed by a hypersonic shockwave that circled the globe, leveling forests and triggering earthquakes of a magnitude that has never been experienced in human history. The very ground would have rippled like water. The impact in the shallow ocean displaced an unimaginable volume of water, creating a mega tsunami. A wave, perhaps taller than any skyscraper, raced outwards from the impact zone at the speed of a jetliner,
scouring coastlines clean for thousands of miles and flooding entire continents. But this was only the beginning. The molten debris that had been blasted into the sky began to rain back down across the globe. Trillions of tiny, superheated glass spheres re-entered the atmosphere, heating the air to oven-like temperatures and igniting continent-spanning wildfires. The rain of fire was a global scourge, a deadly storm of stone and flame that turned the planet's surface into a furnace. Today, the Chicxulub crater lies buried beneath millions of years of sediment, invisible from the surface. But in seismic scans of the Earth's crust, it remains, a silent circular scar. It is the crime scene, the irrefutable evidence of the day the world burned, the day the 160 million year dynasty of the dinosaurs was brought to a sudden, violent, and cataclysmic end. The initial moments of the Chicxulub impact were a maelstrom of fire, blast waves, and colossal tsunamis, a swift, violent purge of life on a continental scale. But the true engine of global extinction was not the initial blast. It was the long, grim twilight that followed. The most devastating effect of the impact came not from fire or flood, but from a profound and persistent darkness. The collision threw vast, unimaginable quantities of pulverized rock, ash, and soot from the global wildfires high into the stratosphere. There, above the weather, this debris spread around the planet, coalescing into a thick, uniform shroud that effectively blocked the sun. For months, and perhaps for several years, the world lay in a state of perpetual twilight. This was the impact winter. Photosynthesis, the fundamental process that powers nearly all life on Earth, shut down. The planet's green engine sputtered and died. Plants, starved of sunlight, withered and rotted. The lush, vibrant forests of the late Cretaceous, filled with the world's first flowers, turned into silent, skeletal graveyards. This triggered a catastrophic, cascading collapse of the entire global food chain, a systematic failure of the planet's biological supply chain from the bottom up. First, the great herbivorous dinosaurs, the Triceratops, the Hadrosaurs, the Ankylosaurs, that depended on a constant supply of fresh vegetation, began to starve. Their immense bodies required a massive daily intake of energy, and with their food source gone, they were the first of the giants to fall. As the herbivores vanished, the apex predators, including the mighty Tyrannosaurus rex, soon followed. Their own food supply had disappeared, and in a barren, lifeless world, their size and power became a liability, not an asset. The delicate web of life, woven together over 160 million years, unraveled with shocking speed. The fossil record shows this as a stark, brutal line in the rock strata, a sudden silence in once thriving ecosystems. The extinction was not limited to the dinosaurs. In the seas, the giant marine reptiles like the mosasaurs and plesiosaurs disappeared. In the skies, the entire dynasty of pterosaurs, the masters of the air for 150 million years, was wiped out. Countless species of invertebrates, plants, and microscopic life were erased from existence. In total, this single event triggered the extinction of more than 75% of all species on Earth. It was one of the most severe mass extinctions in the planet's history. The world that emerged from the long, dark winter was a quieter, emptier, and profoundly different place. The thunderous footsteps of the sauropods were gone. The chorus of the hadrosaurs had fallen silent. The reign of the dinosaurs was over. The catastrophe had reset the balance of power on Earth, indiscriminately wiping the slate clean. Survival was not a matter of strength or size. It was a matter of luck,
and of being small and adaptable enough to weather the apocalypse. In the silent aftermath, in the dark and the cold, the stage was now set for the meek, the survivors who had lived in the shadows of the giants, to inherit the earth. In the desolate, post-apocalyptic world left behind by the Chicxulub impact, the great filter of extinction had done its work. The giants were gone, their immense bodies unable to withstand the collapse of the global food supply. The dynasty that had ruled for 160 million years had been decapitated. And yet, the story of the dinosaurs was not truly over. Not every dinosaur perished in the global cataclysm. A single, small, feathered branch of the theropod lineage, a group of animals that we now call birds, managed to endure the long night. Their survival, against all odds, is one of the most incredible stories of resilience in the planet's history. They were the heirs to a fallen empire, and their descendants carry that legacy to this day. The question is, why did they survive when their larger, more powerful relatives were wiped from existence? The answer lies in a suite of strategic advantages that were perfectly suited to a post-apocalyptic world. Their small size was a critical asset. In a barren landscape, their lower food and energy requirements gave them an edge over their multi-ton cousins. Their ability to fly was another decisive advantage, allowing them to travel vast distances to find scarce, isolated pockets of food and shelter. But perhaps their most important survival tool was their diet.
Many early birds had evolved beaks and could consume seeds and grains. In a world where fresh vegetation had withered and died, seeds were a perfect, durable food source, a storehouse of energy capable of lying dormant for years, waiting for the sun to return. While the great herbivores starved, the seed-eaters had a lifeline. This survival means that in a very real biological sense, dinosaurs never fully vanished. Every sparrow hopping on a sidewalk, every eagle soaring on a thermal, every penguin navigating the Antarctic seas, they are all direct descendants. They are living, breathing dinosaurs. The link is not metaphorical. It is a direct, unbroken genetic lineage. The hollow bones, the feathers, the brooding behavior, even the wishbone found in a Thanksgiving turkey are all inherited traits that trace their origins back to their Mesozoic ancestors. The dynasty did not end, it transformed. It shrank, it adapted, and it took to the skies, launching a new wave of global colonization that continues to this day. This incredible transformation was foretold in the fossil record long before the cataclysm. In the 19th century, a fossil was unearthed in Germany that seemed to straddle two worlds. Called Archaeopteryx, it had the sharp teeth, clawed fingers, and long bony tail of a dinosaur, but it also possessed the fully formed aerodynamic feathers and wings of a bird. For decades, it stood as the perfect transitional fossil, a bridge between two great ages of life, offering a stunning glimpse into how reptilian arms could evolve into avian wings. It was a prophecy written in stone, a preview of the evolutionary path that would ultimately prove to be the salvation of the entire dinosaur lineage. When the asteroid struck and the world fell into darkness, it was the creatures that had followed this path, the small, feathered, and adaptable avian dinosaurs, that carried the legacy of their entire 160 million-year dynasty through the fire and into the new world that dawned after the long night. And so, our strategic analysis of the lost world of the dinosaurs comes to a close. We have journeyed across an almost unimaginable gulf of deep time, from their humble beginnings in the Triassic period to the fiery, apocalyptic end of their reign 66 million years ago. We have walked beside titans that stood as tall as buildings, their footsteps shaking the very foundations of the earth. We have peered into the microscopic world of fossilized pigments to resurrect their lost colors, and analyzed the faint chemical signatures in their teeth to trace their epic continent-spanning migrations. We have moved from seeing them as simple, scaly, terrible lizards to understanding them as a vibrant, complex, and stunningly successful global dynasty. A dynasty that mastered every terrestrial environment, from the polar darkness to the equatorial forests. We have seen how their success was built on a sophisticated and diverse portfolio of strategic assets. It was built on the doctrine of overwhelming scale, in the form of the colossal sauropods, the heaviest land animals in Earth's history. It was built on a relentless evolutionary arms race, which produced the living tanks of the ankylosaurs, the specialized weaponry of the stegosaurs, and the awesome bone-crushing power of the Tyrannosaurus rex. But their dynasty was also built on subtlety and intelligence, on the coordinated pack-hunting tactics of the raptors, the long-range communication networks of the hadrosaurs, and the tender, devoted parental care that ensured the survival of the next generation. For 160 million years, they were the undisputed rulers of this planet. A reign of such immense duration that it reduces all of human history to a fleeting, momentary flicker. Their legacy is a profound and humbling lesson in perspective. They remind us that the world we inhabit is merely the latest chapter in a very, very old story. Their footprints, pressed into ancient mud and hardened into stone, are a permanent record of a power that once held the entire world in its grasp. Their bones are the fallen monuments of a forgotten empire. And their eventual fall, a cataclysm delivered from the cosmos, is a stark reminder that even the most dominant and enduring dynasty is ultimately vulnerable. The asteroid did not just end an era, it triggered a violent, planetary-scale dynastic succession. The old guard was swept away, clearing the stage for the two groups that would inherit the new world. The mammals, our own ancestors who had survived in the shadows, and the avian dinosaurs, the last heirs of the fallen empire. That legacy still beats in the wings of every bird that takes flight today. The sparrows in our cities, the eagles in our mountains, the hummingbirds in our gardens. All are living reminders that the story of the dinosaurs is not truly finished. They are the proof that endings are not always endings. More often, they are transformations. The dinosaurs' world gave way to our own, just as each day gives way to night, and each waking thought eventually drifts into the realm of memory. They are a testament to the fact that life is vast, resilient, and endlessly surprising. They challenge us to consider our own fleeting moment on this planet, and the legacy we, in turn, will leave behind, etched into the deep geological time of the Earth.